This is a historical result of all the penny spin experiments I've done since before 2006. Now, what I've done up there is I've given you, it's a little bit hard to look at, but we'll see it graphically here momentarily. You see the sample size drawn in one column, and the number of heads next to that, which is the same thing I did with you guys. You guys were 260 and 130. So you've got N and X. Here's P hat. I didn't know how to make the symbol in Excel, so I just called it P hat. 0.43, 0.39, 0.42, 0.43, 0.45. Notice how, except for you guys, you got exactly 0.5. Very, very few other classes, 0.51 right there. But very, very few other classes got anywhere near 0.5. You guys and that 0.51. I say near. We'll get to that, what I mean by near in a second. You can ignore this stuff right here. But this is the computation I had Excel doing, which is essentially what we did on the board back here. This is a graphical representation. This is a graphical representation of those ranges of values, P hat plus or minus the margin of error. So if you will, these are the margins of error drawn out that P hat sits right in the middle of. Now, I've got these lines right here. You can't see them, I can slide them out. The lines under are incremented at 0.25, 0.5, 0.75, and 100%. What do you notice about quite a few of these ranges of values? What do you notice? Let me feed that question with an auxiliary question. When I asked you originally, what's the chance of getting heads on a penny spin, you said 50%. Would most of those intervals agree with your claim? No, most of them would actually disagree with your claim, wouldn't they? For example, this guy right here, fall 2006. When we did that in fall 2006, it looks like we got from, I can't tell which one's which actually. I think it's this one here. We got between 33% and 33.5 to 44.5%. Well, that's not 0.5. That's actually below 0.5, isn't it? 37 to 48. Again, below 0.5. 38 to 48, 38 to 46, 38 to 52. Here we go. 38 to 52. Now, all that shows us, here it is right here, I think. All that shows us is we can't disprove 0.5 because 0.5 is in there. Is this ringing a bell from 243? When you have a range of values of which the value you're interested in or you're thinking it is in there, you can't disprove that it's there. But when the value's not in there, here's 0.5, here's this line right here of 0.5. All these intervals that fell below the line of 0.5, all of those disprove the guess of 0.5. They say, we don't think it's 50% because our results came back low, even with a margin of error. Even with a margin of error attached to it. Almost every single one of the P hats is below 0.5. But you can't report just the 0.5. You have to put the 0.5 plus a margin of error, plus or minus a margin of error. But even with the margin of error, most of these fall in below 0.5. And you guys are the obvious exception. You're the first class ever, besides this one, to land exactly at 0.5 or above it. Now that's interesting to me. How should we deal with your data? How should we deal with your data? What would you do with all this data?
I think I would add it up and find the average.
I would too, Cassie. That's what it is right there up top. If I take all the data from all the classes and put it together and create one P hat, I get a P hat of 0.44. And the margin of error on that 0.44 is that wide. Now compare that width to all these widths. Why? Let me ask a question. Why are the widths even changing? Why are they going like this?
Number of people in the class.
Okay, let's say that nice and loud, please.
Number of people in the class. Number of spins.
So the more people, what happens?
Longer line.
Actually, the more people, the shorter line.
Shorter. Why is that?
Oh, because it goes
That's a great question. Why is that?
It's because it singles out towards the average or the center.
Yes, it does. It does, but Cass is 100% correct. As we draw more and more samples, we're getting a better look at the center. We learned that, we kind of justified that on the first day when we said P hat does a pretty good job of targeting P. But why so we have accuracy. What you're hitting at is accuracy. What I want to talk about is precision. The narrower the intervals, the more precise the interval. So how are we picking up precision? And there's a mathematical reason, And there's also a non-mathematical reason. The mathematical reason is actually behind this screen on the board. Remember the formula for margin of error? What was in the denominator?
And
N. As a denominator of a fraction gets bigger, what happens to the fraction itself? It gets smaller. It gets smaller. So as your n gets bigger, notice the large n values, it's kind of hard to see over there, I have to slide over a little bit. But the larger n values, here we go, 140, 152, 230, here's 230, that little skinny guy right there, right? But the small n value, 63, very wide. Now that 63 right there, notice how the 63, that particular confidence interval touches 0.5?
Yeah.
And therefore you kind of put your hands up and you go, I'm not really sure I can believe that it's not 0.5. Well, if we went out and asked, if we spun 100 more pennies, if we spun 100 more pennies, and we got the same percentage, 0.43, out of 100 more penny spins, what would happen to that interval, friends? It would go like that, wouldn't it? And then it wouldn't be touching 0.5. That makes a big assumption, YouTube world. That makes a big assumption. It makes the assumption if we spin 100 more pennies that we still have a p-hat of 0.43. Nobody guarantees if I spin 100 more pennies, I'm going to get 43 out of those 100 to come back heads. See what I'm getting at here, friends? See what I'm getting at here? But I am guaranteeing you this, if you can get a large sample size, this is why a larger sample size, as long as your data is good, is better than a smaller sample size. Larger is better than smaller as long as your data is good.
because it's more precise.
Because you get more precision. You get accuracy for free, but you get precision with larger sample sizes. Yes, and that's a function of that n in the denominator. Thank you, Kaylee. Perfect. You guys buy that? Is that believable-ish? I'm getting there. Believable. Okay, good. Good, good, good. So, here's a question. Why? Why does this appear to be happening? Why are we getting heads so infrequently? Somebody actually hinted upon this in class last time. I forget who it was. Somebody over here. You ever looked at a penny before? Probably not. Because we don't use them that much anymore.
Heads is heavier, so.
Heads is heavier.
Yeah.
Heads is heavier, and this is my theory anyway. When you spin a penny, and you get it spinning on its axis, inertia kicks in. Object in motion tends to stay in motion. More massive objects will stay in motion longer. Heads keep spinning, if you will, and spins itself right down. Tails gives up. Says, to hell with this, I'm done. So you get more tails because head spins itself into the ground. That's a theory. I have no idea how to test it other than this. But year after year after year after year, 0.44 is the average. So yeah, Cassie, I agree. Average it all out. What's interesting though is some of them do touch 0.5. Do those disprove my theory about the pennies? Not really. Not really. They disprove it in your sample. But here's the deal, and I want to make sure we start and restop this again.